Here we go, new unit, and really kind of launching into um, a lot of what we're going to be doing for quite a bit of the rest of the school year. We're going to talk a lot about functions in this class, a lot of different kinds of functions, how those relationships exist. Functions are special kinds of relationships. And so what I wanted to start off with was just, kind of making sure we're all on the same page in terms of understanding what functions are, what the notations are like, what we do with them, what they mean, so that we can then talk more specifically about the different types of functions that we're going to look at and how they're all related to each other. This is all about relationships. From here on out, it's going to be about relationships. You're looking for things that are in common and things that are different between all these different types of functions, all these different type of math relationships that we're talking about. Now, functions just in general, okay? A functional tool is something that works for us, right? If your car functions properly, then you can drive it places, right? If it doesn't function, then it doesn't work properly, right? A calculator is an example of a function if it works properly. If I push the 8 key, then I should see these little dashes that appear on the screen that make an 8. And that should happen every single time I push the 8 key. In fact, that's the only thing that should happen when I push the 8 key. I shouldn't push an 8 key 3 times and one time get an 8, and one time get a 7, and one time get a 9, and one time get a 2, and then get 3 8s in a row and then a 5. That's not functional for me. That doesn't help me in that sense. So this idea of a functional relationship is that you have some input action linked with some specific output action, right? If I push the 8 button on the calculator, I expect to see an 8 show up on my screen. If you're typing an essay and you're typing letters on your keyboard, you expect to see those letters show up on the screen to make the words in the sentences that you want to communicate what you're trying to say. It would not be a functional computer for you if those letters did not link to the keys you pressed on the keyboard, okay? So there's an input and an output that are linked together, and when that works in a specific way, that relationship that exists there, push a button, get a result, or plug in a number, get a specific picture on a graph, that relationship that is consistent is a functional relationship. That's the idea of the word, okay? So just so you have that kind of in your brain as we continue to work through all of this. Now, there are, when we take numbers and we just group them together, we can call them any kind of a relationship, okay, or a relation. And so let's just jot that down. Relations are just numbers grouped together for any reason, or no reason. Maybe I just want a bunch of random numbers, but I'm going to put them together in a group. And I guess maybe that is a reason. It's a group of random numbers, but there's no connection to those random numbers or between those random numbers other than the fact that they're random, right? Okay, and so we could call that a relation of numbers, right? Now, when we have a particular set, which is a grouping of, right? When we have a grouping of ordered pairs, let's make sure we're clear. When we talk about ordered pairs, we most usually represent this with an X and a Y, right? It's a pair of numbers in which the order in which we write them matters, okay? Okay, we can show this relationship or this set of ordered pairs as a table, as a mapping diagram, as a graph, or expressed as an equation. Now, the two that we're going to work with the most are going to be the graph and the equation, right? And I've given you this language before. This is going to be the head side of the coin. This is going to be the tail side of the coin. And the idea would be to flip back and forth between the equation and the graph, knowing that those two things are different representations of the same relationship. Okay, now the set of X values, let's underline that or highlight that, however you want to do that. The set of X values is called the domain of the function. And the set of Y values is called the range of the function. We're going to talk a lot about domain and range. When we have a relationship that has distinct points, this point in space and that point in space and this point in space and that point in space and only those points in space, we call that a discrete function or a discrete relation. And when we have connected lines that flow all the way through, then we call that a continuous relationship. Continuous, yes, okay, continuous relationship. Okay, now, the literal definition of a function, right, is that it's a relationship or a relation in which each element of the domain is paired with exactly one element of the range. All right. Now, when we do set notation, we're going to do like a little squiggly like this. These are called braces. And then within the set notation, we're going to have a set of ordered pairs. So like, for example, if we had the ordered pair 0, 1, and then we would separate that with a comma. And then we had the ordered pair -5, 2. And then maybe we had the ordered pair 6, -2. And then maybe we had the ordered pair 5, -7. And then we would close our set. That would be the relation or the set of ordered pairs. So there's 4 items in that set. And that would make up a discrete relation because we're talking about just this point, just this point, just this point, and just this point. That's why it would be discrete. Okay? So it's not a continuous path. Right? Now, let me give you an example of what is not a function, and then we'll talk about it more specifically. So let's take a set here, and let's say that we have -7, 2, and then we have 6, -1, and then we have -3, 9, and then we have 6, 2, and then we'll close our set like that. Okay, so you'll notice in our first function, our set, every x value, or all the sets of the domain, here, 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 and here, that's the domain of that function, okay? They're all linked to their own unique output. X is input, y is output, and so each one has its own unique output. However, over here, you can see that this 6 and this 6 are linked to 2 different outputs. That can't happen. That is not a function. That is an example of what makes this a non-functional relationship. When we have 2 inputs with different outputs. That would be, I push the 8 button, and sometimes I get an 8, and sometimes I get a 4. Well, that's not functional. That doesn't help us, right? 8 needs to be linked to the picture that looks like an 8, and only that. Okay? And so that would be the result for us in that case. Now, visually, we can determine whether or not we have a function on a graph using something called the vertical line test, which I'm sure you guys have seen before. Let's kind of do an example of that. So what I want you to do is, as best as possible, you're just going to create a straight pathway like this. And we'll put a couple of arrows on that straight pathway. And then what we would do in the vertical line test is we would run a vertical line down our graph. So vertical would look like this. Okay, and if we could take that vertical line right there and we could move it across our graph, left and right, either way, as long as that vertical line only hits the graph one time, we have ourselves a function. So for example, that vertical line hits the graph right there. Keep in mind, when I say the graph, I'm referring to this line right here. That's the graph, right? These two make up the coordinate plane. That's where we draw the graph. So we're clear on the language, right? Okay, the graph is the picture. The coordinate plane is the place where we draw it, okay? All right, so we can continue to make that vertical line, and you can see that each time, it's only going to hit our graph one time each. Okay, this would be an example of a continuous function, specifically a continuous linear function, right? Makes a straight line. Linear function, we have that relationship. Okay, now, to the best of your ability over here, draw yourself a circle.
You know those professors that can like do more with their wrist? Yeah.
Now, if we do the vertical line test on a circle, like you can see that that vertical line hits the circle here and here. And if that vertical line hits the graph more than one time, it is not a function. Okay? Now, I want you to just ballpark something with me, right? Let's just pretend that this vertical line I ran through here runs through at +3 on the x-axis, okay? Let's call that vertical line x equals 3. Then we could ballpark this and we could say, all right, well, maybe this is 3, 4. And maybe this is 3, -3 here. See, in that situation, you can see that we have the same x value, but a different y value. See, visually, when we have the same x and different y's, they're going to line up on the same vertical line at different heights along the way. That is not a function. So this right here, if you were to plot those points, you would have a vertical line that goes at +6. It would pass through +2 and -1 out here. That would make it not a function. Make sense? Vertical line test is how we see our visuals over here, okay? Now, this is also an example of a continuous graph, but because it's not a function, we would just call this a continuous relation. Get it? So it's still a pairing together of numbers. There's still an equation that ties this continuous graph together. We're going to be working with those, okay? But it's not a function. Difference between a relation and a function.
So, like, just a plain vertical line, that wouldn't be a function?
Good question. Yeah, so a vertical line is not a function. Yeah, exactly. Yeah, a vertical line is not a function. How about a horizontal line then? Horizontal line would be. How about a sloped line? Okay, so anything that has a slope, because horizontal lines have a slope of 0, right? Any sloped line would be a function, but a vertical line has an undefined slope and is not a function. Good question. Okay, so let's do a little practicing. On the head side of the coin, right? This is the head side of the coin, number side, okay? I want you to find the domain, the range, and tell me whether this is or is not a function, and you're going to write your domain and range in set notation. Okay, so you'll do like a little set here, and then you'll list out your domain, and then you'll close your set. And let's say this, for domain and range, sets are written left to right, least to greatest. Okay, so you go ahead and find your domain, your range, and whether you think it is or is not a function. Okay, go ahead. Write it out. Let's see what you do. Give it a shot. There's your domain and range. So to get your domain, you just take all of your x values and you write them least to greatest, left to right. To get your range, you take all of your y values, least to greatest, left to right. In this case, there is no evidence in this discrete function that any x is linked with any other y, because again, remember, this is just a point, a point, a point, and a point. That's it. That's all that exists in this, and since there's no x's partnered with different y's, then yes, this is a function. Okay, good. If we have repeat numbers in our domain or our ranges when we're writing them in set notation, we do not repeat them in the set. So if you have multiple numbers and you're writing them in set notation, we do not repeat them. Okay, go ahead and do number 2. You're doing number 2.
Yeah. No, I'll explain that.
Numbers here.
Yeah, I spend more time writing my braces than anything else. They are true.
Okay, so that's the head side of the coin. Just for sake of interest, let's do a little mini scratch graph over here. Let's just do a little mini scratch graph over here. And let's plot these points, and we're just going to ballpark them, right? So if the first one is at +5, +2, I'm just going to ballpark like here-ish. And then -3, +4 would be maybe here-ish. +5, -6 is probably going to be down here-ish. And then 8, 0 is probably going to be out here-ish, like that. So I'm just taking these points and I'm putting them on the graph, right?
Yeah,
This is a discrete graph because we're just given those points and only those points, right? But you can see here, if we ran the vertical line test, we do not have a function because we have repeating x's with different y's. Okay, so this would be a discrete relation. A discrete relation, not a function. Put a little asterisk in front of that like we did. Discrete relation. Okay, good so far? Let's do number 3. Find the domain and range. This time, instead of giving a set notation, you're given a table of values. Okay? Find the domain and the range and whether or not it is or is not a function. Go ahead. All right, did you get a function? Yes or no?
Yes.
Yeah, this is a function.
You got 2 slopes,
Right? Well, two y's. Okay, so let's just for sake of interest, let's just graph this out to see what it would look like real quick. Right, again, this is another discrete function, right? So I'm just going to do a little xy graph down here. Let's put some points on there. So 7, -8 is probably going to be like way down here. 2, +3, maybe like here. 0, -1, it's going to be like here. And then -4, +3 is going to probably be here. And so in this case, you can see that we have repeating y values here and here, but they're linked with different x's, right? And so graph-wise, that creates this type of a setting. And that's okay. So we'll say this is okay because the same height, which is our y value, can be paired with different x's. That's an okay thing. What we can't have is the same left and right distance or the same domain paired with different y's. Okay? Good? Last one, number 4. Go ahead, you finish that one up. Domain, range, yes or no function. And I want you to write whether it's discrete or continuous at the bottom.
It's really easy. It's beautiful. They're not brackets.
Okay? Is this discrete or is this continuous?
Continuous.
This is discrete.
There's distinct points on the line.
Because you're only given this point, this point, this point, and this point. You would not make a line or curve or circle or parabola or cubic function. You wouldn't make any of that there because you're only given 1, 2, 3, 4 points. That makes it a discrete graph. Okay? Good so far? All right. It is a discrete function. It's not how many you need. It's how the information is given to you. So here we're told that this set of pairs is the function. That means it exists of 1, 2, 3, 4 things. Now, when we're given an equation that allows for any input and output to link together, then we would have a continuous graph because it would stretch on because there's no limit to the inputs that can be linked to the outputs. Okay? All right, now let's talk about mapping diagrams. We're not going to see them a whole lot, but you need to know what they are. You need to be able to be familiar with them. Okay? So mapping diagrams, it's another way of saying what x's are partnered with what y's. Okay? So in this case, -4 is partnered with 0, whereas 5 is partnered with 7 and 9. Okay?
No, it's fine.
No, it's fine.
No, it's fine.
Well,
No,
it's
there's
fine.
5
Just
is too big.
it's not a function.
Oh, you're right.
And over here, 2 is partnered with 7 and 13 is partnered with 4. It's the x partnering with the y. So what I want you to do for 5 and 6 is find the domain, the range, and tell me whether they are or are not functions based on the mapping diagrams that you see there. Go for it. You should have come up with these right here for your domain and range. Take a look. The first one is not a function, while the second one is a function. This would be an example of something that doesn't pass the vertical line test because we have 5 linked with +7, but we also have 5 linked with +9. That means at 5 on the x-axis, it would cross through 7 and 9, and that vertical line would render that not a function. Still discrete, though, because we have an individual set of points given to us, just written differently. Okay? And then over here, we still have a 2 partnered with a 7 and a 17 partnered with a 7. But again, as we saw before, it's okay to have the same y partnered with different x's. That creates that horizontal placement of your discrete points. So that's okay because horizontal lines pass the vertical line test, making them functions. Good? You know what you're looking for on sets? All right, let's step up our game a little bit, okay? So we're going to start and we're going to work a little out of order here, all right? You're going to want a couple of colors for this section. So if you don't have some highlighters, come grab a couple of colored pencils, but you're going to want 2 colors for this and make them colors that stand out. Like don't do orange and red, okay? Like do blue and orange so that they're clear, okay?
You know, like this. Wide blue.
Okay. We are going to start on number 10. Okay? So, if I were to do the vertical line test on number 10 and I were to take my vertical line and I were to drag it over my graph, is this a function? No, this is not a function because anywhere from here to here, I'm going to hit that graph more than one time, right? And so that is not a function. Any one example of that makes that not a functional graph, right? That elliptical looking shape there. Okay, all right, good. So I'm going to just set my vertical line over here. So we could say that, no, this is not a function. Now, is this a discrete graph or is this a continuous graph?
Continuous.
This is a continuous graph. And the reason it's continuous is because this solid line that you see here that goes in this circular looking shape, it includes every fractional point that you could think of. If I could zoom in all the way as far as I could zoom in, and we were talking about this distance in here, we could keep making that smaller and smaller and smaller and smaller and smaller and smaller, smaller, smaller. Keep going all the way down fractionally. And yet every point that's on that line is included in the function. And that's what makes it continuous. And when we talk about the domain of our function and the range of our function, we have to speak of that in terms of its continuous nature, right? So in our previous examples, where we were listing out our domains and ranges, it was just these individual points on that graph. Well, now we got to figure out a way to say we need all of the domain numbers that exist anywhere in this relationship here. And the way we do that is we set limits, okay? So we talk about the farthest or the lowest domain limit and the highest domain limit that our graph covers, okay? So like, for example, what would be the lowest domain number that our graph reaches to? What do you guys think? -2, right? Okay, and so what we're going to do is we're going to take one of our colors, and we're going to draw a line with one of our colors down here, and we're going to make a note that that is at -2. That is the farthest our graph goes down the domain, right? Again, remember, domain is our x, right? And so we're talking about our left and right. So the lowest domain is going to be the farthest point left on our picture. Okay? What would be the highest domain that we have?
5, 4, 5.
1, 2, 3, 4. It goes out here to this line, huh? All the way out there. Okay, even though it's not on the x-axis, it does go all the way out there, right? Okay, so that's going to be 5. So let's draw a limit line out here so we can see it real clearly. Okay, and let's say that that's a 5. Now, we're not talking about height here. We're just talking about on this line here, could I pick a point and have it be on that graph? Like, for example, if I pick the domain number 0, is there a partner on the graph for domain 0? Yeah, it's right here, right? That would be whatever the domain is, 0, right? How about for -1? Is there a partner for domain -1 on the graph? Yeah, it's right here, right? That's my partner for domain -1, right? How about for +2 3/4?
Absolutely.
Yeah, well, 2 3/4 would be about here-ish, right? So there's actually 2 points on the graph, huh? Right? If I go here, I can go here, right? And so my domain is really going to be all of the x values that stretch from my furthest here to my furthest here. And that's how we have to write it. That's how we have to express it. And one way that we can do that is to use inequality notation. So we can say that the domain sits in between the two limits of -2 and +5. See what I did there? This is called inequality notation, right? And this statement right here is the head side of the coin that tells us that we can pick any x value, and if it sits between -2 and +5, including -2 and +5, because that's a solid line at those exact points, anything that stretches in between -2 and +5 will make this a true statement. That's how we would write our domain in inequality notation. Good? Pretty okay? All right, then why don't you try to draw the range lines? That would be how high does the graph go up and how low in your other color. Give yourself a number for them and see if you can write it in inequality notation. Give it a shot. Let's see what you can do. Okay? The range is what are all the y values that our graph stretches between. Go ahead, give it a shot. And you should have come up with a range like this. Did you use a y?
Yes.
Good. Okay? Because if you're talking about range and you use an x here, tick, 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 points start coming off.
Is that a small markdown or is that a point markdown?
That's a small markdown. It's not not a misconception. Sort of. Maybe a 0.2, 0.4. Depends on if I see it multiple times. Okay, well that was pretty easy, right? You get it? That covers all of the height numbers between -2 and +4, and all of the left and right numbers between -2 and +5. Domain and range for continuous graphs must be represented in an inequality notation, or I'm going to show you another way to do it in set notation too, but set notation is a little bit trickier. It's easier to make mistakes on. But I'll show you how to do it, and you can decide which one you want to use, okay? I think inequalities creates a better understanding though. Okay, we good?
Yes.
All right, let's do number 7, okay? Why don't you create some limit boxes for your domain and your range. Let's see what you can come up with. Okay, go ahead. With that. Now, the limit boxes aren't necessarily needed in this situation, right? But it's a good confirmation, it's a good practice for you to see that here's the low end of your domain and here's the high end of your domain. Here's the low end of your range. Here's the high end of your range. But this is not a continuous graph. This is a discrete graph because it's just these individual points, and then it does not pass the vertical line test, so it is not a function.
So if the graph's discrete, you have to use that certain method in terms of if I look at it together with something.
Yes, because we're talking about only this point and only this point and only this point, and not a stretch of things in between those points. And so because we're not talking about everything in between, but just those points, we would list those specific domain and range numbers. Whereas when we have the continuous graph, we can't list everything because we could keep making those fractions infinitesimally small. We would die before we finished writing them all, so that we have to write them in a inequality notation saying bigger than this but smaller than that. Okay. All right, good so far? Okay. Number 8. Let's see what you got.
So there's no limit.
For number 8.
Ooh, that is true. Wait, that is true.
Be a hint.
Yeah.
It's not infinite.
It's not infinite. Yeah. You did it wrong.
Yeah, I know.
This is what you should have come up with here. All right, so we bring in this idea of negative infinity versus positive infinity, right? So that means that if we're dealing with domain, anything bigger than 0 is going to be positive infinity, while anything less than 0 is going to be negative infinity. Same thing on the y-axis. Anything greater than 0 is positive infinity, and then less than 0 is negative infinity. So then the question is what do we say about the domain? Okay, well, is there any point where I could not pick an x value and have it partner up somewhere on that line? Every x value that you could think of, we could go around and I could pull the classroom for x values. Every x value is going to have a y partnership because this arrow continues on and this arrow indicates continuing on, right? So that means every number works. And so the way we state that is we say all real numbers. All real numbers. Now, mathematicians are lazy. I've told you that before. So we always come up with these little notation things. And so one of the ways that you will see all real numbers abbreviated in notation is kind of this double R. So I just do it with a double R like that. So you can use that. If you actually see it like in like printed, it'll be like the whole thing will be doubled all the way around, but that just gets complicated and messy. So if you just do a double bannered R for me like that, that can be your abbreviation for all real numbers.
It's just double R.
Okay. How about the range? What would be the range for this one? Yeah, it'd be the same thing because there's no y value that doesn't have an x value, right? So again, our range would be all real numbers.
Sweet Naga, right? That's all real numbers.
Okay, now, can we write that in inequality notation? Yes, we can. It would look like this.
Yes, Lucy, see, I'm smart.
Watch this, though.
So no longer is equal to, it's just...
What did I do different with that one?
It's not equal to.
Yeah, because infinity is not a value, so we can't say it's equal to a value. So we just have to say that our range has to fit somewhere between negative infinity and positive infinity. Make sense? Another way that we could write that would be like this. Okay, so just make a note. This is what we call inequality notation, where this is what we call set notation. By the way, is this a function? Yes or no?
Yes.
Yeah, this is a linear function, right? Okay, so this is a function. By the way, let's come down here to our original one. So I told you that this was written in inequality notation, right? We could write that in set notation. In set notation, it's going to look like this. What did I do different? Brackets. What do the brackets mean? No. This means it's included or equal to. This means it's included or equal to. True. So if we had a graph that looked like this, well, in this case, if it goes on to infinity, it would be parentheses. But if we had a solid point, that's a good point. Let's change that. So let's say we had a graph that looked like this. Then this would be parentheses. This would be parentheses on one end and brackets on the other. Not included. Yeah. Okay. All right. Number 9. Start with your limit boxes. That's why we do those, because it'll help you visualize what you need to say about your domains and ranges. Okay? And again, I'm going to use mostly inequality notation. Okay? But again, you can use set notation, but it's just you'll have to be able to make that translation. Okay? All right, let's see what you can do. Go ahead, give it a shot. Here's what you should have come up with for domain and range.
I got that.
So there's no top limit, so we then would just say, well, our domain has to be greater than -4 or equal to, because it's a solid representation there. And if it was a hollow dot there for some reason, which we're not going to get too much into those because we got other things to do, but then it would not be an or equal to. Bracket -4 comma infinity parenthesis would work for your domain. Yeah. So here, that's good. That's good, Tosh. Thanks for bringing it up. Okay, so if you wanted to write this one in set notation, right, it would be bracket -4 comma infinity parenthesis. That's how you would write that one in set notation. Make sense? Because it's including the -4. And then we have our infinity can't be included, so it has to be a parenthesis. Good. Okay. So domains and ranges of continuous graphs using our inequality or set notations. Questions before we move on? Everybody good? Okay, now, we will eventually get to the point where you can look at these graphs, know what they are, and know what to do with them. You really actually should, for 12, 13, and 14, you should be able to create a visual image. Go ahead, do that right now. 12, 13, and 14, create a visual image in your mind of what those should look like. In fact, better yet, let's not even create a visual image. Let's just draw a quick and dirty graph. Here we go. So 12, 13, and 14, we'll just give ourselves a little coordinate plane here, like that. Little coordinate plane here, like that. Little coordinate plane here, like that. And we'll just do quick and dirty graphs of what you think those should look like. Give it a shot. Come up with your pictures looking something like that right there.
Oh, I got it. Yeah.
Okay, so go ahead and do domain, range, and function for 12, 13, and 14. We'll start with that. Go ahead and do those. Domain, range, and function for 12, 13, and 14. Go ahead. Should have come up with these for your domains and ranges. Take a look and see how you did. Okay, so notice with the vertical and the horizontal line, the y value is always the same. It doesn't get bigger or smaller, so we would just say y is always equal to -7. There's only one value for that range, okay? Now, let's say you had one that you didn't know what it looked like, okay? Like, maybe you know what this one looks like, maybe you don't, okay? But you can always use our friendly little tool in Desmos, and you just go there and you type in the equation y equals -x² + 3. All right, so I'll leave that up there for you for a second. Write your domain, range, and function for that one.
both continuous.
It is indeed.
Alright, for X is
Here's your domain, range, and yes or no on function. All right?
Well.
So that graph continues to extend out left and right, but it maxes out at a height of +3, but it goes down forever and ever, so it does continue to trend towards negative infinity in the range. And then because it is always growing outward, right, that's going to have that function relationship, that vertical line test. All right, good so far? All right, cool. All right, next up. Okay, we are going to hit the highlights of this page. We are not going to do all of them, nor do we need to. But there are some important things that we need to do. We need to talk about function notation, okay? Reading this is super, super important that you understand how this works, okay? Now, hopefully by now you have all seen something that looks like this. This is the function machine, right? And in the function machine, the x is the input, and the y is the output. And then the math that exists inside the function machine, that's the rule that ties the input with the output. So just like the rule of push the 8 button, get an 8 on the screen, there's a rule that ties that together. I want an 8. There's like little complicated zeros and ones and little digits to put the little dashes on the calculator to give you that. Those are the rules that guide that. This is the rule that guides this relationship, okay? Now, this is linear notation right here. Function notation is going to look like this. Okay, it is still the same machine. However, this right here is read f of x. Okay, so this notation right here is read f of x. Or think of it this way. It is the output f at the input x. That's what that's reading. Okay? So your input, again, is still going to be your x, and your f of x, or g of x, or h of x, or b of x, or d of x, or whatever, is going to be the output. So let's jot that down. X is our input, and f of x, and it can be any letter, g of x, d of x. A could be the input. It could be g of a. We can use any letters we want. And actually, we would use them to change the labels on things so that we could keep multiple graphs in one coordinate plane organized. Okay? So the way that we do this is, if this is the rule that ties things together, and I'm asking you to find this. This is a math question. That math question says, tell me the output of the function when the input is -3. That's what the math question tells you. Tell me the output of the function when the input is -3. Okay, so the way we would do this is we would say, well, f of -3 is equal to 2, open parentheses, plus 7. At which point we would write a -3 in here. Right? Sorry.
I actually did this though. So
Okay, so f of -3 is equal to -6 plus 7. F of -3 is equal to 1. This is read the output of the function when the input is -3 is 1. Now let me show you another way that we write this. Maybe one you're more familiar with. Those two things mean the same thing. This is ordered pair notation. This is function notation. Okay? Super important you can read that. All right? Now, let's do number 1 right here, okay? And you'll notice that here you're given 2 different kinds of functions. This is the f of x function, and this is the g of x function, okay? You're being asked to find f of negative 9. The value of the f function when the input is negative 9. Ready, go. Have come up with f of negative 9 is 31.
Splendid.
Okay, so we're taking our inputs and we're plugging them in and we're getting our outputs. Like, now, we're not going to take the time to do this, but I'm just going to have you write this down. Start in fracts. Stay in fracts.
Like fracking.
Something like that. We're not against fracking here in math class. We don't discriminate. Fractions and decimals are numbers too. If you start in decimals, stay in decimals.
We would learn that in like 8th grade.
Okay, you got it? Do number 4. Ready to go.
Wait, negative.
Should have come up with negative 113. Yeah. Highly recommend using open parentheses when you set up your function problems, then drop your number in. That way you don't get confused on your signs.
That's what I got. This.
What do you think you would do with this question right here?
Yeah, I got negative. The final answer. No, you're negative 49.
You would do g of 12, right?
Right.
And then multiply by 2. Okay, all right. Let's go to the back side.
Shall we?
Let's take a look at number 13. Wait, number 13 is a little different. It's saying f of x, not f of like negative 3 or g of negative 9.
We just go 34 equals 3.
Okay, keep in mind what this says right here, okay? Output equals 34. Find the input. Well, if we're using the above equation and this right here is the output and the output equals 34, then we should just be able to go output equals 3x plus 19. Right? This time we're starting with the y and we're going backwards to find the x. They're still connected by the same rule, so we should be able to go one direction or the other, just like we're turning around in geometry and walking on the same sidewalk, both directions. Right? Subtract 19 from both sides. We're going to get 15 is equal to 3x. We're going to get 5 is equal to x. Or we could think of this as heads, tails. Heads, tails. I'm gonna ask for both. I mean, in this case, the question is asking you to find x, so I want to see x equals. That would be the answer. But you need to know both of them so that you have that connection. Yeah? Okay, good. Functions. I think we covered pretty much everything you need to be successful.
I say so.
There's a lot of messy, like look at this one down here. Think about what you would do with that one. Well, you would have to plug this in for x here. You'd have to plug this in for x here. And then you'd have to subtract those two when you do all that math. We're going to do that right now, but okay. Let's talk homework. Now we're not going to do any more on that paper. The rest of that paper is not homework. It's just the highlights for us. Talk about everything.
You only use 3 papers. Yeah, there's not funny anymore. I don't get to go.
You didn't finish the thread, by the way.
I'm gonna kill you.
Wait.
You want to do that? No, stop.
All right. So let's talk homework. We're going to do.
You have a problem?
Man,
That's only 3 papers.
Yeah, but yeah.
Oh, we can do all of them. We can do all of them. It's not that much. Front side will go by real fast. Yeah. And there's not a lot of overkill on the back. It'll give you a chance to practice with some fractions, some compound ones, some multi-term ones. So yeah, we'll do them all. Okay. Thank you. Test on Thursday. So this is due. Do I see you Monday? Do we have a Monday? Yeah, we have Monday, right? Okay, yeah. All right. So this will be due Monday. All right. Yeah, so you got a little extra time. Even more reason to do them all. Good.
Calculator.
No, I do 2 times. No, I